Big ideas? Short lessons.
Imagine putting every contact, photo, password, game score, and message you own into one enormous digital drawer. The computer could store all of it. Storage is the easy part. But now I ask for one thing: find Amma's phone number. With no arrangement, you may have to pull out one item, then another, until you finally find it. And as the drawer grows, the search grows with it. That is the problem data structures solve. They don't magically create information. They arrange information so the things we need to do next, find, add, remove, compare, or reorder, don't become painfully expensive. A data structure is an agreed way to organize data, together with rules for using that organization. Think about a kitchen. Plates go in one cupboard, spoons go in a drawer, spices sit on a rack with labels. The cupboard doesn't make a plate better. The label doesn't change the spice. The arrangement makes the next action easier. In a program, we make the same kind of agreement. Where will each item live? How will we reach it? And what must move when something changes? That agreement is the structure. An array, a stack, a queue, a tree, and a hash table are different answers to the same question. How should we arrange this information for the work we expect to do? Before choosing a data structure, don't ask which one is the best. Ask, what will I do most often? Will I read an item by its position? Search by a name? Add new items at the end? Remove items from the middle? Always take the smallest item first. These actions are called operations. A structure is useful because it makes some operations cheap, but that usually makes other operations more expensive. Numbered lockers make it easy to jump directly to locker 27. A pile of trays makes it easy to take the top tray. A waiting line makes it fair to serve the person who arrived first. None of these arrangements is universally best. Each one is good because it matches a particular job. Picture a supermarket. Grouping all the fruit together helps you find bananas quickly. But whenever a new delivery arrives, workers must spend time putting every item in the correct place. Now imagine the store leaves every new item beside the entrance. Restocking becomes very fast. Finding bananas becomes terrible. The store cannot optimize both jobs with the same careless arrangement. Programs face the same trade-off. We can spend effort while inserting data so future searches become faster. Or we can make insertion easy and accept more work during search. Memory is also part of the bargain. A structure may answer quickly because it stores extra labels, links, or empty space. Choosing a data structure means choosing which costs matter for this particular problem. This brings us to Big O notation. The name sounds mathematical, but the first idea is simple. Big O asks, as the amount of data grows, how does the amount of work grow? We usually call the number of items n. If our contact list grows from 10 names to 1,000 names, what happens to the number of steps needed to find someone? Big O is not mainly a stopwatch. Two computers can finish the same job in different times. It also ignores many small details so we can see the shape of the growth. Does the work stay roughly the same? Does it grow with the number of items? Does it grow much faster than the number of items? Constant doesn't mean instant. Linear doesn't always mean slow. Big O tells us how an approach scales, especially when small examples become enormous ones. Here are 4 growth shapes you'll see often. O of 1 is constant work. Imagine a labeled drawer. Whether the room holds 10 objects or 10,000, opening the drawer marked spoons is still one direct action. O of log n is repeated having. Think of finding a word in a dictionary by opening near the middle, then keeping only the half that can contain the word. 16 possibilities become 8, then 4, then 2, then 1. Even a million sorted items can be narrowed down in about 20 halvings. These are gentle growth shapes. More data adds little, or sometimes no, extra work to the operation. O of n is linear work. If socks are mixed in an unsorted basket, you may check each sock once. Twice as many socks can mean roughly twice as much checking. O of n squared often appears when every item must be compared with every other item. 10 items create around 100 possible comparison steps. 1,000 items can push that toward 1 million. The notation is just a short label for the shape of that growth. Let's make the work visible. Our contact list contains Amma, Ben, Chen, and Dina. We want Dina. A simple search recipe says, for each name ask, is this Dina? If not, continue, we check Amma, then Ben, then Chen, finally Dina. In the worst case, 4 names require 4 checks. 1,000 names may require 1,000 checks. That is linear growth, O of n. If the names are sorted, we could repeatedly cut the remaining range in half. That changes the search toward O of log n. Or we could organize contacts around their names using a hash table, aiming for near constant lookup on average. but paying different costs in memory and organization. Same information, different arrangement, different work. So here is the rule to carry into every lesson in this series. Don't memorize a data structure as a diagram. Connect it to a problem. What information are we organizing? Which operations happen most often? What happens to their cost as the data grows? A good structure makes the important work manageable. A poor match can make a simple task expensive, even when the code looks clever. Big O gives us the language to discuss that growth. The structure gives us the arrangement that creates it. In the next lesson, we'll begin with arrays. Why numbered positions make reading fast, why inserting in the middle can be slow, and why arrays appear almost everywhere. Until then, remember, organize for the job.